Let's get right into math assignment number 12. This is the last video of this series at this time. I might add more later, which is why when you go to my website, please register so you can log in. If there's any updates available, we'll use your email address to send you any updates, any PDFs to add to what you've purchased. The Water Math Challenge. A treatment plant is equipped with a basin 94 feet in length, 62 feet in width, with a depth at the upstream side of 12 feet and 15 feet on the downstream side. The flow through the plant is 0.825 million gallons per day. The water in the basin has been dosed with 31.65 pounds per day of a coagulant aid. The effluent feed is 35.78 pounds per day of chlorine for disinfection. After an hour of contact time, the free chlorine residual is 2 milligrams per liter. What is the surface area of the aeration basin? Question number 1. Well, surface area is area in square feet. And this is a rectangular basin, so the basin has a length, a width. It also has a depth, but we're looking for length and width. So our formula is going to be the length in feet multiplied by the width in feet. Let's take that formula and plug in the information we need to complete our calculations. The length, 94 feet in length. The width, 62 feet. We have unit of measure of foot here, a second one here. That's the unit of measure we're looking for. Let's multiply 94 times 62 equals 5,828 square feet. The best answer is C. Question number 2. This is the same scenario from the first question. Calculate the volume of the basin in cubic feet. We need the volume in cubic feet. So we want volume in cubic feet equals the length in feet multiplied by the width in feet multiplied by the depth in feet, depth or height. So let's rewrite that formula to make our calculations here. We have length, which is 94 feet. Our width, which is 62 feet. And then we have depth. Now the interesting thing about this plant is this basin has a depth on the upstream side of the plant at 12 feet. On the downstream side it's 15 feet. So we have to calculate if the entire basin was 12 feet in depth, and then make calculations for the entire basin as if it was 15 feet in depth, and then take an average of those. So let's start with the upstream side. The upstream side of the basin, which is, here's the upstream side, is 12 feet. So we are looking for volume in cubic feet. We have foot here, 2, 3 of them. That's the unit of measure we're looking for. So let's make our calculation. Let's multiply 94 by 62 by 12, and that's going to give us 69,936 cubic feet. Now, when you're taking your certification exams, keep in mind that if you make this calculation, that answer may be one of the choices. It'll be incorrect, because we still need to calculate volume for 15 feet if the entire basin was 15 feet in depth, and then average this out. So let's start the second calculation here. And again, we want length in feet times width in feet times the depth in feet. I want to remind you again that I do this every time. This is my process. This is what I do during exams. I write it out. It only takes a few seconds to write out the formula that you're going to use, and that's going to be your guide. The length is 94 feet. The width, 62 feet. And the depth of the downstream side is 15 feet. So let's multiply that out. 94 times 62 times 15, that gives me, well, before I do that, let's double check. We have foot, 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 1, 2, 3. That's the unit of measure I'm looking for. And my answer is 87,420 cubic feet. Now we need an average. So let's take the 69,936 cubic feet, add it to 87,420 cubic feet, and that's going to give us, I'm going to add 69,936, and that's going to give us 157,356 cubic feet. Now we're going to take that. Let's make sure I'm getting it all in the video. We're going to take that 157,356. We're going to divide it by 2. Divide by 2, that gives us 78,678 cubic feet. Our best answer is G. Question number 3, how much water is in the basin? Again, this is the same scenario, same question, but we just have several questions based on that information. So, how much water is in the basin? How much water is in the basin? How much water? Well, so this is the same basin from question number 2. This is the answer key from question number 2. We know that there is 78,678 cubic feet. So let's write that down. Let's write down that we know this. volume equals 78,678 cubic feet. So I want to get the volume in gallons. How much water is in the basin? Actually, the choices are in gallons. So let's write a formula. The volume in gallons equals the volume in cubic feet multiplied by our conversion factor, 7.48 gallons per cubic foot, all right. That's our formula. That's what we're starting out with. So let's write volume 78,678 cubic feet multiplied by 7.48 gallons per, I just wrote 7.48 gallons per cubic foot. I'm going to leave that mistake in there so you can see it. I make mistakes. Generally, I find those mistakes very early in this process because I'm going step by step. I do it the same way every time. Repetition is super important. So let's cross cancel. Let's get rid of this cubic foot and this cubic foot. I'm left with gallons. That's the unit of measure I'm looking for. So now it's just simple multiplication. 78,678 multiplied by 7.48 gallons per cubic foot, and that is going to give me 588,611 gallons. 588. Well, look at that. The best answer is C. Okay, now we're going with question 4. Same scenario as the previous questions. There's a few more to go. Calculate the dose in parts per million of coagulant aid. We don't want to do the chlorine, so let's just highlight the water in the basin has been dosed with 31.65 pounds per day of coagulant aid. That's what we're looking for right there. Let's focus on that so we don't accidentally grab the feed of the chlorine. So calculate the dose in parts per million of coagulant aid. Parts per million is the same as milligram per liter. We want feed in pounds per day. We need the flow, million gallons per day. We want the dose, milligrams per liter, and multiply all that by 8.34 pounds per gallon, the weight of water. So the feed is going to be coagulant aid. All right, let's fill in all this information that we need. So we've already highlighted 31.65 pounds per day of coagulant aid. The flow through the plant is 0.825 million gallons per day. We're looking for the dose. So let us we'll go ahead and write this down right here. We have 31.65. Going to multiply 0.825 times 8.34. That's going to give us 6.88. 31.65 divided by 6.88 gives us 4.6 milligrams per liter, which goes right there. The best answer is N. Number 5. Calculate the dose of chlorine used for disinfection. Dose of chlorine. Well, just right here we see the effluent feed is 35.78 pounds per day of chlorine for disinfection. Chlorine. I want to make sure that stands out. All right. So, again, we're going to start with the feed. Pounds per day. The flow in million gallons per day. The dose in milligrams per liter. And then we need the weight of a gallon of water, which is 8.34 pounds per gallon. Let's fill in the information that we have. 35.78. We have the flow through the plant. Flow through the plant is 0.825. 0.825. We're trying to figure out what the dose is. So we will take 35.78. Let us 0.825 times 8.34. The flow times the weight of water, 6.88. 35.78 divided by 6.88, and that is equal to 5.2 milligrams per liter. The best answer is M. Moving along very well here. Question 6. What is the chlorine demand? What is the chlorine demand? Well, we know that the demand equals the dose minus the residual. Real briefly, I want to tell you that when we're disinfecting the water, as the water moves into the disinfection process, we will dose it with chlorine. That's the dose. That's the chlorine we're going to give it to achieve disinfection. At the end of that process, before the water leaves the process, we're going to test it and we're going to pull a residual, a free chlorine residual. In some cases, we might be getting a total chlorine residual and a free chlorine residual. I will review the differences of that in a later video. The difference between the dose and the residual is the demand. It's how much chlorine it took, the amount of chlorine required to disinfect the water to a point where we feel confident the water is safe to discharge. So now we know the dose from a previous question. We know these are known that the dose is 5.2 milligrams per liter. Where am I getting that information? I'm getting it from question number 5. This is the answer key. When we calculated 5.2 milligrams per liter as the dose. Remember, this is the same plant, same scenario. So let's rewrite this equation. We want the demand in milligrams per liter equals the dose, which is 5.2 milligrams per liter, minus the residual. The residual is, the free chlorine residual is 2 milligrams per liter, 2.0 milligrams per liter. Oh dang, I just put them. Well, let's make it look like this. Dose minus residual. So let's use this color. (5.2) minus 2.0, that gives us 3.2. We don't need a calculator for that, do we? So the answer is 3.2 milligrams per liter. S is the correct answer. The last question for this theoretical plant. Question 7, what is the pressure in PSI reading on the pressure gauge at the downstream side of the basin? Well, we're looking for pressure in PSI, downstream side of the basin. We know that the downstream side of the basin is 15 feet on the downstream side. So we want pressure in PSI equals the depth of the water in feet multiplied by our constant, 0.433 PSI per foot. Let's rewrite that with all the right parameters in there. Equals depth on the downstream side, 15 feet, over 1 multiplied by 0.433 PSI per foot. Let's make sure we're doing this right. I can cross cancel out foot here. I'm left with PSI. That's the unit measure I'm looking for. Let's do some math. Let's do some calculations. 15 times 0.433, that gives us 6 point, we'll call it 6.5. It's 0.495. Let's just round it up to 6.5 PSI. Look at that. W is the correct answer. You've been assigned to paint the floor of a room which measures out to 675 square feet. 1 gallon of paint covers 50 square feet. How many 5-gallon containers of paint will you need? We need to know how many 5-gallon containers. 5-gallon buckets of paint. We're going to need to buy more paint than we actually need to do the job because the buckets come in 5-gallon increments. Is that the correct way? So paint by the gallon equals, let's see, the area in square feet should we call that total coverage? And we know that 1 gallon equals 50 square feet. Let's rewrite this. I want to know, so the total area is 675 square feet. So I'm going to write down 675 square feet over 1. We're going to divide that by 1 gallon of paint covers 50 square feet. So the room measures out to 675 square feet. Each gallon covers 60 square feet of paint per gallon. There we go. Now it makes a lot more sense. After I cross cancel out square feet here, I'm left with gallon. That's the unit of measure I'm looking for. So now it's just a matter of how many gallons am I going to need? 675 divided by 50, and that equals 13.5 gallons of paint. We're not done yet. So how many 5-gallon buckets do I need? How many buckets do I need? And these are in 5-gallon buckets, right? So I have 13.5 gallons that I need, and these are 5-gallon buckets or containers. This gallon is gallon over 1. This is gallon over buckets. Let's cross cancel those. I'm left with buckets. This is my unit of measure I want. 5-gallon buckets. 13.5 divided by 5-gallon buckets, and that's going to give me 2.7 buckets. I can't buy 2.7 buckets, but I can buy 3 buckets. I'm rounding up because I need more paint than I need to purchase more paint than I actually need to do the painting job. 3 buckets. The correct answer is B. Love this question. Question number 9. A single piston reciprocating pump has a 6-inch diameter piston with a 6-inch length of stroke. If it makes 16 discharge strokes per minute, the pumping rate is... Let's remember what a piston is. So we have a piston. It's circular, it has a diameter, and it has a gear of some kind that drives it up and down through a cylinder. Very tight tolerances, drives up and down through the cylinder. That's a really crude drawing, but I think you get the idea. Piston drives up and down through this cylinder. As it pulls down, it pulls chemical in. As it pushes up, it pushes chemical out. There's a check valve on one side here, a check valve on the other side. That's the influent side, which I spelled incorrectly, the effluent. There would be a pipe, check valve, injects the water or the chemical. As the piston drives back up, it goes through another check valve, which forces out this way to the effluent side. A little more detail than you needed probably, but we're going to start with that. Now, the formula we want to use is because we want the pumping rate. We want the pumping rate. Let's highlight that. We want the pumping rate. How are we going to figure out what the pumping rate is? Well, I want the pumping rate and that's going to be in gallons per minute, right? GPM equals gallons per minute. We're working with a cylinder. We're working with a round object, a cylinder. So we're going to start with 0.785. And we need to know the diameter. We need to know diameter in feet multiplied by the diameter in feet. Because we're looking for a volume, we don't have a length. However, what we do have, well, we do have a length, excuse me. So we have a 6-inch diameter. we have a 6-inch length of stroke. So let's do length, which is, we'll need it in feet. I think you kind of see where I'm going with this. Now, it makes 16 discharge strokes per minute. That's very important information. Let's highlight that. 16 discharge strokes per minute. And the answer, the unit of measure we're looking for, is in gallons per minute. There's a minute right there built into it. So if it had said 32 discharge strokes per 2 minutes, we could convert that down to 1 minute, 16 strokes per minute, to get this correct. But we're going to put down on here stroke, 16 per minute. And because we're looking for gallons, we want our conversion 7.48 gallons per cubic foot, because look at this, 1, 2, 3, we're looking for cubic feet also. We want to eliminate that because a foot unit of measure is not in the final unit of measure that we're looking for. 7.48 gallons per cubic foot. So let's fill in all this information. 0.785. The diameter in feet is, whoa, hold on, 6 inches. That's the wrong unit of measure. I need feet, but it's in inches. So very quickly we can write 6 inch. That's the diameter. We know that there are 12 inches per foot. This inch is over 1. So inch above the division line at the top, inch above the division line on the bottom, means that we can cross cancel. Cross cancel, and we get 6 divided by 12 equals 0.5. 0.5 feet. So now we'll continue on with our filling this all in the formula. 0.5 feet over 1. Diameter. 0.5 feet over 1. The length. The length, here it is 6 inches. We need it in feet. We've already done the math here, so 0.5 feet over 1. We have stroke, 16 strokes per minute, and our conversion factor, 7.48 gallons per cubic foot. Let's cross cancel. We have foot, 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 cubic feet. We have gallons, we have minute, that's the unit of measure we're looking for. So now it's down to a calculation. 0.75 times 0.5 times 0.5 times 0.5 times 16 times 7.48, and that gives us 11.74 gallons per minute. My best answer is B, 12 gallons per minute. Question 10. What is the difference in temperature in degrees Fahrenheit between the water source and the processed water in a storage tank? If the temperature of the water source is 12.6 degrees Celsius and the water in the storage tank is 16.3 degrees Celsius. Boy, oh boy, oh boy. What is the difference in degrees Fahrenheit? That's what we're trying to figure out. Well, I know that the formula from the ABC formula conversion tables, the math formula sheet, we want, and I always start off this way, what is the difference in temperature in degrees Fahrenheit? Degrees Fahrenheit. Well, we go look it up, and we're going to find degrees Fahrenheit. The formula is degrees Celsius. We're going to multiply that by 1.8, and then we are going to add 32. The water source, this is the water source, equals 12.6 degrees Celsius. The water source is 12.6. I'm going to multiply that by 1.8, add 32. 12.6 times 1.8. I'm going to add 32, and that's going to give me 54.68 degrees Fahrenheit. Don't be surprised if you're taking your operator certification exam and you have a similar question and you see this number as one of the choices. If you choose that number, it's going to be wrong. This is an easy point to get because you know what your next step to do is. The storage tank, this will be the tank, equals degrees Celsius times 1.8 times, or plus 32. That's our formula. The temperature in this storage tank is 16.3 degrees Celsius. We're going to multiply that by 1.8, add 32, 16.3 times 1.8, and that gives us 29.34. We're going to add 32, and that gives us 61.34 degrees Fahrenheit. We're still not done. And that might be one of those choices too, but let's go ahead and finish this. We have 54.68 degrees Fahrenheit. We want the difference, so we're going to subtract that from 61.34 degrees Fahrenheit, and that's going to give us 61.34 subtract 54.68 gives us 6.66 degrees Fahrenheit. The correct answer is B. That's the closest answer. Question 11. I love heat problems. These are easy. If the desired dose for chlorine is 2 milligrams per liter, how many pounds of chlorine per day will be needed to treat 2.1 mgd, million gallons per day? How many pounds per day, pounds of chlorine per day? Oh yeah, this is fun. All right, feed problem. Draw out our pie. We have feed in pounds per day, flow, million gallons per day, dose, in milligrams per liter times the weight of a gallon of water. That's pounds per gallon. Let's write in all the information we need. If the desired dose for chlorine is 2 milligrams per liter, that's the dose. How many pounds per day will be needed to treat 2.1 mgd? I've got my coworkers texted me on a Sunday morning asking about training. I love that. I will check on the schedule and get back to you. That's awesome. Love it that my operators want to get training and certifications. Let's do the math. Flow multiplied by the dose, multiplied by 8.34 pounds per gallon. 2.1 times 2 times 8.34 gives us the feed in pounds per day, which is 35.03 pounds per day. The best answer is B. Question number 12, another feed problem. What is the chlorine dosage in milligrams per liter if 4.6 mgd is treated with 55 pounds per day of chlorine? What is the dosage in parts per million? I got you, buddy. All right. Draw out our pie. We have feed, which is in pounds per day. Flow, 1,000,000 gallons per day. Dose, milligrams per liter. The weight of water, 8.34 pounds per gallon. Let's fill in the missing information. What is the chlorine dosage? Dosage is what we're looking for. 4.6 million gallons per day. Treated with 55 pounds per day. We know that this is 55. We're going to multiply 4.6 times. This is X, so this is 8.34. That gives me 38.36. 55 divided by 38.36. That's going to give me 1.43 milligrams per liter. The best answer is A, 1.4. Question number 13. How many pounds per day of liquid alum? How many pounds per day of liquid alum are used if the flow rate is 12.7 mgd and the dosage is 8.25 pounds per day? That's fun. We want feed in pounds per day. Let's draw out the rest of our pie here. We have flow, 1,000,000 gallons per day, dose, in milligrams per liter, times 8.34 pounds per gallon. The flow rate, 12.7 mgd. The dose, 8.25. This is easy. 12.7 times 8.25 times 8.34 pounds per gallon, and that gives me 873.8 pounds per day. But hold on a sec, we're not done yet. And look at this. If we take this answer and choose choice A, it's going to be incorrect. Why is that? Well, it's because this 873.8 pounds per day is at 100% purity. You see right here, the purity of the alum is 48%, which means that we are using some type of chemical, most likely it's liquid, to carry the alum to the treatment process. And 48% of that chemical is actually alum. So we need to know how much of that liquid chemical we need in pounds per day to account for the purity of that chemical, which is 48%. So we want the feed in pounds per day. I'm just going to use this. The feed in pounds per day equals 873.8 pounds per day at 100% purity. We're going to divide that by 48%. Well, before we divide by 48%, let's convert 48% to a decimal. So 48% divided by 100. %, divided by 100 equals, that's the decimal, 0.48. 0.48. Think about it as a dollar bill. If I have a dollar bill, 48% of it is 48 cents. Look how it's written. 0.48 is the same thing as 48 cents. So we'll take 873.8 and divide that by 0.48, and we are left with 873.8 divided by 0.48. That's going to give us 1,820.42 pounds per day. That's the unit of measure we're looking for. And the correct answer is C. Watch that video again if it doesn't make sense. It's all right here. Again, we're looking for purity. They have a chemical that's 48% alum that we have to dose into the water. To get 48%, or to get this 873.8 pounds at 100% purity, we're going to have to dose with a much larger volume of that chemical to achieve this 873.8 pounds. 14, we're moving right along. A 2-foot diameter pipe, 3.2 miles in length, was disinfected with chlorine. If 82.9 pounds of chlorine was used, what was the dosage in milligrams per liter? So we want the dosage in milligrams per liter. Well, let's start with our pi. We want feed in pounds. Notice how I'm not writing pounds per day. The reason I'm not writing pounds per day is because we're talking about a 2-foot diameter pipe, 3.2 miles in length, that was disinfected with chlorine. This is a pipe that was built. It was capped on both ends with probably a blind flange. On one of those, they created a way to fill the line full of chlorinated water, and on the other side, they allowed air to escape. They capped it off. Well, they took a chlorine residual once they filled up the pipe. They capped it off. They gave it a certain amount of time to disinfect that brand new stick of pipe, 3.2 miles in length. When after a certain or a given time, they took another chlorine residual, another grab sample, and depending on that residual determines if the pipe has been disinfected properly or not. So this is a one-time thing. So we want feed in pounds. We want volume in million gallons. So this formula is just slightly different than the one that we've been using, the feed formula. Because again, we just want the volume of the pipe, but we want it in million gallons. We have dose in milligrams per liter, and then the weight of water, 8.34 pounds per gallon. Okay, so that we know 82.9 pounds of chlorine was used. 82, boy, that is the ugliest 2 I've ever seen. 82.9 pounds of chlorine was used. 82.9 pounds. What was the dosage in milligrams per liter? Well, before we figure that out, we need to figure out what the volume is of this pipe. That's fun. We know, because we look at our ABC formula conversion table, the math formula sheet, that 1 mile is equal to 5,280 feet. Since we know that, we can calculate the volume of this pipe in gallons. So a pipe is a long, narrow cylinder. Because it's a cylinder, we're going to start with 0.78. What am I doing, Bert? 0.785 times the diameter in feet. Multiply that by the diameter in feet again, multiplied by the length of the pipe in feet. And then we're going to multiply that by our conversion factor, 7.48 gallons per cubic foot. 7.48 gallons per cubic foot. So we'll rewrite that formula, putting in everything, all the information we need to calculate the volume in gallons. 0.785 multiplied by the diameter, which is 2 feet in diameter. 2 feet over 1. Wow, this is a 2-foot diameter pipe. That's a heck of a pipe. Diameter, 2 feet over 1. The length. So that's 2 foot in diameter. The length is 3.2 miles. Well, I need the length in feet. So we got to do some calculations here to figure out the length of the pipe in feet instead of miles. So I want the length in feet equals the length, 3.2 miles, times our conversion factor, 5,280 feet over 1. Excuse me, feet over per mile. 5,280 feet per mile. All right. So above the conversion, or above the division line, we have mile here. We have it here below the division line. We can cross cancel that out. We're left with feet. That's the unit of measure we're looking for. Let's multiply 3.2 times 5,280, and that is going to give us 16,896 feet. So we can put that length down here as 16,896 feet. Let's get back to completing this formula. We're going to multiply all that by 7.48 gallons per cubic foot. We're looking for gallons. We have foot, foot, and foot. That should be over 1. Cross cancel out that cubic feet. We want gallons. We're left with gallons here. So let's multiply that out. 0.785 times 2 times 2 times 16,896 times 7.48, and that gives us 396,839.73 gallons. That's the unit of measure we're looking for. Well, hold on. We need this unit of measure to be in million gallons, not gallons. How do we do that? We just simply divide by 1 million, and that gives us, look, here's that number, 396,839.73 divided by 1 million gives us 0.396. Let's call it 0.4 million gallons. 0.4 million gallons. Plug that in right here, 0.4 million gallons. That gives us, we've already got 82.9. We'll take that 0.4, which is already here. We're going to multiply that by 8.34, and that's going to give us 3.31. 82.9 divided by, here's the division line, 3.31 gives us a dose of 25 milligrams per liter. The correct answer is D. There's several steps involved, and this question is the perfect example of why we are always aware of the units of measure. The units of measure in this were given us in feet, in miles, pounds, milligrams per liter. There's several of them we're dealing with here, and we just have to be mindful as we're calculating everything out that we're making conversions as necessary, as we did here, from miles to feet. Question 15, convert 350 degrees Celsius to degrees Fahrenheit. Easy, we know this, we've done several of them. We need some more conversions from Celsius to Fahrenheit, or Fahrenheit to Celsius. It's my dyslexia jumping in there again. So our formula is degrees Fahrenheit equals degrees Celsius times 1.8 plus 32. 350 degrees Celsius. Multiply that by 1.8. We're going to add 32. Just slamming it around. Times 1.8 times. Whoop, whoop, whoop. Boy, did you see that? Let's start over again. 350 times 1.8 equals 630. I'm going to add 32, and that's going to give me 662 degrees Fahrenheit. The correct answer is D. The best, closest answer. Question number 16. Which of the following is the same as parts per million? Parts per million, it's 1 part per million. Well, liters and million gallons per day, that doesn't add up. 1 gallon per million gallons per day is parts per million. 8.34 pounds per 1 million pounds. Well, that doesn't make any sense. 8.34 pounds is the weight of water, or a gallon of water. If that said per million gallons, that would be a part per million. That's not correct. And I can tell you right now, looking at milligrams per gallon, or excuse me, milliliters per gallon, that's not correct. The correct answer is, I want to highlight it, 1 pound per 1 million pounds. That is parts per million. We use milligram per liter very, very commonly in the water and wastewater industry as our unit of measure for parts per million. Question 17. What is the area of a circular clarifier with a diameter of 22 feet and a depth of 12 feet? We have area of a clarifier. The most important thing there is circular. It's a circular clarifier. So let's start with the area. The unit of measure is square feet. This is a big round circular cylindrical object. So we want 0.785. We're going to multiply that by the diameter in feet and multiply it by the diameter in feet again. This is area. We want it. This is area. We want it in square feet. We don't need the depth. We just need a diameter of 22 feet. Quite often you will receive more information than you need to solve a math question. A lot of other questions too. 22 feet. Multiply by the diameter again. 22 feet over 1. Dang it. See what I did there? I should have wrote diameter 22 feet over 1. Diameter 22 feet over 1. 1.785. Let's just cross that out. That's a mistake. Just want to do it right. I want to do it correctly. We have foot here, foot here. That's the unit of measure we're looking for. Let's do the math. Let's make the calculation. 0.785 times 22 times 22. All that effort for some very quick button pushing. 379.94. Boy, that's like 380 square feet. The best answer, closest answer is C. We're going to have a few questions in this water math challenge that we haven't covered in previous videos. This is one of them. If a run of pipe is 828 feet and it drops 13 feet in elevation, the rise of the run is? What is the rise of the run? Well, understand here that we're laying a pipe. This pipe is several 20-foot sections, which add up to 828 feet. And because we like to use gravity to move water instead of pumps, gravity is very inexpensive compared to purchasing pumps and having to pump water everywhere we go, even downhill. The upstream side of the pipe is going to be at a higher elevation than the downstream side of the pipe, giving it a slope. That slope allows the water to flow at a velocity calculated out by the engineer who designed the pipeline. They want to get enough of a slope that if there are solids in the water, they won't settle out. The velocity will be fast enough that it won't allow solids to settle out in the pipe and cause a blockage later on. We don't want such an extreme slope that the velocity of water exceeds a certain velocity. If the water is moving too fast, too quickly, at too high a velocity through the pipe, it'll actually scour the inside of the pipe. It'll act like sandpaper. Anything that might be in the water, even if it's dissolved minerals and things like that, just the flow of the water through the pipe is going to start wearing out the pipe from the inside out. We don't want that either. So the simple formula to determine the drop or the rise is rise over run. The rise, or in this case, the drop, which in the field The guys in the field, you very often hear them calling it the drop. And just a side note, when you're building a pipeline, you want to start with the lowest elevation first and build the pipeline going upstream towards the source. That way you are assuring that as the pipeline is being built, you're constantly having the project surveyed to make sure that we're maintaining the proper slope. So rise over run. In this case, that means we want to know what the rise is. We want the rise. We know that the drop is 13 feet, which is the drop, 13 feet in 1, and we're going to divide that, here's the division line, over the run. The run of the pipe is 828 feet. That's the length of the pipe. The run equals the length. So let's cross cancel this foot, and that's going to give us a number. It has no unit of measure other than it's the rise. So 13 divided by 828 gives us 0.016. Let's just call it that. 0.0157. I'm just looking at that here. C is the correct answer. Question 19. 2 columns of water are filled completely to a height of 88 feet. Column A is 5 inches in diameter. Column B is 5 feet in diameter. What will the pressure gauges located at the bottom of each column read? Well, again, we have a column here, a large cylinder. And this one is 5 inches in diameter. We have another column, which is much larger. And this one is 5 feet in diameter. Does it matter what the diameter is? It does not. What matters is the weight of the water. Here's the water inside the tank. What matters is how much water is pushing down on the bottom of the tank. It doesn't matter what the diameter is. It could be a lake. What matters is water surface to the bottom, or in this case to the pressure gauge, which might be a foot or two above the bottom. So 2 columns of water, we want a pressure at the bottom of the column. So we know that PSI equals the depth in feet multiplied by our conversion factor. I should have written that right there, but 0.433 PSI per foot. Well, our depth is 5 feet in diameter. Nope, excuse me. I'm going to leave that right there. That's a mistake. I got ahead of myself. I'm looking for depth. In this case, it's reported as the height, 88 feet. 88 feet over 1. We're going to multiply that by 0.433 PSI per foot. Now let's cross cancel. I have foot here above the division line, foot here below the division line. I can get rid of that. I'm left with PSI. That's the unit of measure I'm looking for. 88 feet times 0.433 PSI. And that's going to give me 38.1 psi. The answer is D. This is a great question. A pressure gauge on a cylindrical tank 32 feet in diameter, 22 feet in height, reads 7.65 psi. What is the water depth inside the tank? What is the water depth inside the tank? Well, we know we want what is the depth. And the depth will be in feet. So we know that there are 0.433 psi per foot. We want to know what the psi is, or excuse me, what the feet are, right? So we have the pressure in psi, and we have our conversion factor of 0.433 psi per foot. Now I can look at this formula and I can say, well, I want my unit of measure when I'm done making my calculations to be in feet. So that means I have to eliminate the psi here and the psi here. Well, up here, psi can be written as psi over 1. Below the division line is psi over feet. So I'm going to be able to cross cancel those out. Let's try that. The pressure (7.65 psi over foot). Divide that by 0.433. Excuse me, psi over 1. Let's make that correct. The temperature, or the the pressure is 7.65 psi. We write that as 7.65 psi over 1. Our conversion factor is 0.433 psi per foot. Let's cross cancel that out. Psi here, I'm left with feet. That's the unit of measure I'm looking for. Sometimes I get going a little quickly, and that's especially bad when you're dealing with math equations for people like me who struggle with math. Sometimes I have to remember to slow myself down. 7.65 divided by 0.433 psi per foot, and that's going to give me 17.67 feet. The best answer is B. Math should not be rushed. Question 21. How much water in million gallons? How much water in million gallons can a basin measuring 120 feet in diameter and 18 feet deep hold? So I am looking for volume in million gallons equals 0.785. Why am I starting off with that? Well, I see a basin that has a diameter and a depth. The diameter is the key. It's a cylinder. So I start with my 0.785 times the diameter in feet, multiplied by the diameter again in feet. And this is volume, so it's going to take depth in feet. I already wrote the 18 down because I'm a loser. No, I'm not. 0.785. Boy. I'm not sick. I don't have COVID. 120 feet in diameter. 120 feet over 1. We have depth, which is 18 feet over 1. We're not done yet, are we? We have water a million gallons. We need our conversion factor, 7.48 gallons per cubic foot. I have to write that down too. 7.48 gallons per cubic foot. All right, now we got it. So we can eliminate 1, 2, 3 feet, cubic feet. We are left with gallons. Now that's not the unit of measure we're looking for, but to get there, we're gonna have to do one more thing. We're gonna have to divide all this by, let's get the right color here. We'll have to take this and divide it by 1 million. 0.785 times 120 times 120 times 18 times 7.48, and that's going to give me 1,521,970.56 gallons. That's the unit of measure. I need to divide that by 1 million to get million gallons, and I'm going to get 1.52 mg, million gallons. The correct answer is C. And by the way, boy, just a quick note, don't pick C. If you don't know the answer, don't pick C. It doesn't work. What you can do is watch my videos. Watch my videos, print up, purchase the downloads, print these sheets up, practice, practice, practice. Go over it as many times as you need. Go over it the day before you go take the exam. Go through this again, especially those math formulas and equations and calculations that are most difficult for you. Get very comfortable with them. On the day of the exam, last thing you want to do is just sit there and cram. It uses up your brain. You know what you know. Go take your exam and do the best you can. Calculate the pressure in pounds per square inch at the bottom of a tank if the water level is 33.11 feet in depth. We need the pressure in PSI. So we want PSI equals the depth in feet, and we're going to multiply that by 0.433 PSI per foot. The depth, the water level is 33.11 feet over 1. Multiply that by 0.433 PSI over foot. Let's cross cancel. Get rid of that feet, get rid of that feet. We have PSI, that's the unit of measure we're looking for. Excellent. 3.11 times 0.433 gives me 14.34 PSI. A is the correct answer. Question 23. Convert 34 cubic feet per second to GPM, to gallons per minute. I'll highlight that whole thing. That's exactly what it wants us to do. So we want to take cubic feet per second and convert it to gallons per minute. Cubic feet per second, gallons. 7.48 gallons per cubic foot. I know that's going to be a conversion factor. We also know there are 60 seconds for every minute, so we know that that's going to be involved as well. So let's go ahead and write out our formula. We want gallons per minute. We'll start with 34 cubic feet per second. We know there are 60 seconds per minute. Now the reason why I'm multiplying those across is because seconds is below the division line here and above the division line here. I know I can cross cancel those out and get to minutes. Now I'm left with gallons per cubic foot. See how gallon is above the division line here and cubic foot is below the division line? Cubic feet is above the division line here. I want to cross cancel that out because it's not part of the unit of measure I'm looking for. So I'm going to multiply 7.48 gallons per cubic foot. We're going to cross cancel. Let's get rid of that cubic foot. Let's get rid of seconds. I'm left with gallons per minute, which is the unit of measure that I want. 34 multiplied by 60 times 7.48, and that gives me 15,259.2 gallons per minute. 15,300. D is the correct answer, the closest answer, the best answer. Question 24. Calculate the volume of a trench 363 feet in length, 3.5 feet in width, and 6 feet in depth. So we want to calculate the volume of a trench. Well, it's asking for cubic feet. So volume in cubic feet equals, and this is a trench, it's got a length, a width, and a depth. So length in feet, width in feet, depth in feet. That's the formula we're going to use. Let's fill in the important information that we need to make these calculations. The length, 363 feet over 1. The width, 3.5 feet in width. And then we have the depth. 6 feet over 1. Let's check our units of measure. We have 1 foot, 2 feet, 3 feet, cubic feet. 363 times 3.5. I wish I could have made that decimal just a little bit better. And did I hit multiply? Let's try this again. I just want to make sure I've got it right. 363 times 3.5 times, yep, I had it right, 6 equals 7,623 cubic feet. The answer is C. Answer key. We're going to scan that in. Be one of our downloads. Question 25. What is the volume in cubic yards of the trench described in question 24? Volume in cubic yards. Well, if we look back at question 24, we have our answer. Let's talk about what we know. We know that 3 feet equals 1 yard. We know that if we take 3 feet, multiply it by 3 feet, multiply it by 3 feet again, we're going to get 27 cubic feet. We have feet, feet, feet. It's 27 cubic feet. So 27 cubic feet equals 1 cubic yard. And we know that the answer to question number 24 was 7,623 cubic feet. That's also a known. I wrote it up there just to kind of separate it out. So we want volume in cubic yards. Volume in cubic yards equals, let's do volume of the trench is 7,623 cubic feet. We'll put cubic feet over 1. Cubic feet is above. And we know that there's 27 cubic feet per cubic yard, which is right here. So let's divide 27 cubic feet per cubic yard. Okay? Which means that this right here can be expressed as 27 cubic feet per cubic yard. That's what I'm using right here. Let's cross cancel. Cubic foot is above the division line here, which is above the division line here. I'll cross cancel those out. I'm left with cubic yards. That's the unit of measure I'm looking for. You might have to, and you might want to, if you're like me and you struggle with math, you might want to watch this video a couple of times and practice this out. 7,623 divided by 27 equals 282.33 cubic yards. The correct answer is D. Some velocity. Water is flowing through a channel that is 4 feet wide, 1.5 feet deep. If the flow is 10.5 cubic feet per second, what is the velocity of the water? What is the velocity? That's what I want to know. And the velocity is going to be in feet per second. I can tell you that right now because I can see these choices. So I want velocity in feet per second. And that's going to equal, and again, this is in our ABC formula conversion table. If you go to my website, there's a link that takes you there. You can download that formula conversion table for free. You want the 2017 US-Canada version of the formula conversion table. You can select water or wastewater. Get them both. Flow rate in cubic feet per second divided by the area in feet squared. That's going to make sense because when we get the flow rate in cubic feet per second and the area in square feet, 3 minus 2 is 1. We're left with foot. We have second here, second here. Get the right colored pen. So equals flow rate. Flow is 10.5 cubic feet per second. We're going to divide that by the area in square feet. The area we want to do area in square feet equals water is flowing through the channel that is 4 feet wide. And 1.5 feet in depth. Let's cross cancel. Nope, we want foot. That's the unit of measure we want. Let's get our 4 feet times 1.5 equals 6. 6 square feet, so our area is in 6 square feet. Again, we want to take foot cubed minus foot squared, and that's going to give us, it's going to give us foot, right? So let's take flow rate 10.5 divided by area 6, and that will give us 1.75 feet per second. How do I know that? 10.5 cubic feet minus foot squared is going to give me feet. 10.5 feet and divided by 6. 10.5 divided by 6. Okay? We have seconds here, so this will be seconds. 10.5 feet per second divided by 6 gives me 1.75 feet per second. The best answer is A. All right, we're going to work our way through question number 27. A water treatment plant has 6 filters, an average flow rate of 6.1 gallons per minute per square foot. If the plant flow is 70 cubic feet per second, what is the filtration area of each filter? Filtration area of each filter. There are 6 filters. So what we want to do is convert (70) cubic feet per second to gallons per minute. That's how we're going to start this off. How are we going to do that? Well, gallons per minute equals 70 cubic feet per second. Now we know there are 60 seconds per minute. We want to get from seconds to minutes. 60 seconds per minute. Again, why did I multiply it instead of divide it? Well, I multiplied it because seconds is below the division line here and above the division line here. So I know I'll be able to cross cancel that out. Now, I'm also looking for this clue within my formula that I'm building. I see cubic feet and I see gallons. I want to get rid of that cubic foot. And I want to be left with gallons. Well, look at this formula, this conversion factor, 7.48 gallons per cubic foot. Gallons is above the division line, and I don't see gallons in here to cross cancel. I will be left with gallons. Cubic feet is below the division line. Over here it's above the division line. I'll be able to cross cancel that out because I don't need it in the final unit of measure. So I will multiply 7.48 gallons per cubic foot. Let's make sure that checks out. Seconds here, cubic feet here. I'm left with gallon, I'm left with minute. It's the unit of measure I'm looking for. So we're going to multiply that out. 70 times 60 times 7.48. And that's going to give me 31,416 gallons per minute. Now, what am I going to do with that? Well, I know I have 6 filters. And it has an average flow rate of 6.1 gallons per minute per cubic foot. So let's take $31,416 gallons per minute, and we're going to divide that by 6.1 gallons per minute per square foot. Because I'm writing it gallons per minute, you can't just go and write per square foot. But I can take gallons, minute, and I will be left with square foot. Gallons per minute per square foot. Okay? 31,416 divided by 6.1. And that's going to give me 5,150.17.16 equals 5,150.16 square feet. That's the average flow rate for all 6 filters. We need to get it down to per filter. What is the filtration rate area of each filter? So let's go to blue again. Let's take this 5,150.16 square feet over 1 and divide it by 6 filters over 1. Okay. That's square feet per filter. We have that 5,150.16 blah blah blah. We're going to divide that by 6, and that's going to give us 858.36 square feet, and that's per filter. correct answer is B is the closest, most correct answer, 861 square feet. Here's another question. It's fun because it's just logic. You just take it step by step. Question 28, the price schedule for a water system is as follows. 5 cents for the first, 5 cents per 1,000 gallons for the first 10,000 gallons. 4 cents per 1,000 gallons for the next 15,000 gallons. And then it's 25 cents per 1,000 gallons thereafter. Oh boy, contractors. Okay, so considering this information, what would a water system bill a customer who used 35,000 gallons of water during the billing period? Well, the way I like to figure this out is for the first 10,000 gallons, right? First 10,000 gallons. In fact, what is the bill for a customer who used 35,000 gallons? So the first price on the menu, and I'll write it down like this. First equals did I say 5 cents? It's 50 cents per 1,000 gallons. 50 cents per 1,000 gallons for the first 10,000 gallons. The unit of measure is per 1,000 gallon. There's 10,000. So we're going to multiply 50 cents times 10. 0.5 times 10 equals $5. Now we used up 10,000 gallons. So right, 35,000 minus 10,000 leaves us with 25,000 gallons. I have 25,000 gallons, which is more than the 15,000 gallons in the second menu price. The second menu price is 40 cents. And that's 15,000 gallons. So let's take 40 cents times 15, and that's going to give us $6. That's 15,000 gallons. We're going to subtract 15,000 gallons, and that's going to leave us with 10,000 gallons. So the third charge in the menu is 25 cents, 0.25. Let's write this again. 0.25 per 1,000 gallons, and we're left with 10,000 gallons. 0.25 times 10 gives us $2.50. $2.50. That eliminates that last 10,000. So let's add all this together. We have $5 plus $6 plus $2.50. Let's add all that together. 5 plus 6 plus 250 gives us $13.50. The correct answer is C. Question 29. Calculate the surface area in square feet for the inside of a cylindrical, let's do this, surface area inside of a cylindrical ground storage tank, scheduled to be coated for corrosion control, which is 68 feet in diameter 22 feet in height. Include the sidewall, floor, and roof. This is fun. You're going to like this. Now, let's just talk about circumference, diameter, and radius. If I'm looking at the top down to this tank, if I start in the middle and go to the furthest edge, we call that the radius. If I go from one edge to the furthest edge, I call that the diameter. If I start at one point and I go completely around the entire circumference, I will have circumference. Now that we've established that, let's talk about this ground storage tank. This ground storage tank is a cylinder. Now it wants us to include the sidewall, the floor, and the roof. Well, the floor and roof are going to be the same dimensions. We could calculate the area out by using the 0.785 times the diameter in feet times the diameter in feet. But we have to include the sidewall too. Now, if I take the sidewall and I cut it right down, straight down, and then I lay it out flat, I'm going to be left with one giant rectangle, right? We know that the height is 22 feet. But what is the length? We don't know because we have to measure the circumference. So let's go to our ABC formula conversion table. And there we go, circumference of a circle. Circumference of a circle is 3.14 multiplied by the diameter. 3.14 is pi. So let's keep that in mind. Let's go ahead and start working on our formula. We want circumference in feet, and that equals 3.14 pi times the diameter in feet. Okay? We know the diameter is 68 feet over 1. Let's calculate that out. 3.14 times 68 equals 213.52 feet. Feet here, that's the unit of measure I'm looking for, and I got it. So we know the length, 213.52 feet. Let's keep that in mind. So we want to figure the area. So let's start with area in square feet, and we want the sidewall. And we'll just call it sidewall equals the length in feet multiplied by the height in feet. H-E-I-G-H-T. I know how to spell. So let's get length. The length is 213.52 feet over 1 times the height is 22 feet over 1. We have foot here, that gives us square feet. That's the unit of measure we're looking for. So now let's take 213.52, multiply that by 22, and that's going to give us, look at that, 4,697.44 square feet. Now let's keep that in mind. Now we need the square footage of the floor and the roof. There's the roof. The floor is going to be the same dimensions. So we will start with area in square foot, and we will put roof and floor. Now we're dealing with a circular object in 3D. This is a cylinder. 0.785 times the diameter in feet, multiply that by the diameter in feet. 12 square feet, that's what I'm looking for, equals 0.785 times the diameter, which is 68 feet over 1, multiply that by the diameter again, 68 feet over 1. I have feet here, square feet is what I'm looking for. Let's do the math. Now, at this point, keep in mind, I've got roof and floor. So I'm going to multiply that times 2. The inside of the roof, the top of the floor, this is everything in the side of the tank. Include the sidewall, floor, and roof. So this is everything inside the tank is getting coated. Because there's a floor and a roof, I'm going to multiply it by 2. Okay. Let's get rid of that. 0.785 times 68 times 68 times 2 gives me 7,259.68 square feet. Now, let's add this together. We have the sidewall. We have the roof and floor. Let's add them together. We get sidewall equals 4,697.44 square feet. We have roof and floor equals 7,259.68 square feet. Add 4,697.44. That gives us 11,957.12 square feet. What is the best answer? B, 11,960 square feet. Question number 30. Determine the volume of water in gallons for the following distribution system. Volume, gallons. Distribution pipe A was 1,376 feet in length and 3 feet in diameter. Distribution pipe B is 833 feet in length and 2 feet in diameter. The storage tank is 120 feet in diameter with a water depth of 30.73 feet. This is easy. We know that the formula for all three of these calculations is going to be volume in gallons equals 0.785 times the diameter in feet times the diameter in feet times the length or depth in feet. And then to get gallons, we need 7.48 gallons per cubic foot. That's the formula we're going to use. So let's do pipe A. Volume in gallons. Pipe A equals 0.785 times the diameter. 3 feet over 1. Diameter 3 feet over 1 times the length 1,376 feet over 1 times 7.48 gallons per cubic foot. We have feet, 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 cubic feet. We're left with gallons. That's the unit of measure I'm looking for. 0.785 times 3 times 3 times 1376 times 7.48, and that gives me, oh, I hit something wrong. Got a negative number. What did I do there? 0.785 times 3 times 3 times 1,376 times 7.48, and that gives me 72,716.37 gallons. But wait, I'm not done. We need the volume in gallons for pipe B. That equals 0.785 times the diameter for pipe B. 2 feet over 1. Diameter is 2 feet over 1. The length is 833 feet. And multiply that by 7.48 gallons per cubic foot. Let's cross cancel and make sure we're doing this right. We have foot, 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 cubic feet. Left with gallons. It's the unit of measure I want. So let's multiply this out. 0.785 times 2 feet times 2 feet times 833 feet times 7.48, and that gives me 19,564.84 gallons. But wait, we are not done. We need the the storage tank. Volume in gallons for the storage tank equals 0.785 times the diameter. 120 feet in diameter. Water depth 0.73 feet over 1. Multiply that by our conversion factor, 7.48 gallons per cubic foot. Let's cross cancel. 1, 2, 3 cubic feet, gallons. That's the unit of measure I'm looking for. Let's multiply that out. 0.785 times 120 times 120 times 0.73 times 7.48, and that's going to give me, that's 2,598,340, let's go ahead and call it 342 gallons. Okay, we need to combine all of those. We're going to combine, put that right there, 72,716.37 plus, took that one, 19,564.84 plus, we got that one, 2,598,342 equals 2,690,623 gallons of water. Is that choice available? Boy, oh boy, the best answer is C. Very, very close. Question 31, the final question in this video. A well 300 feet in depth and 10 inches in diameter requires disinfection. The water table is 75 below ground level. If the desired dose is 80 parts per million, how many pounds of 12.5% sodium hypochlorite solution are required? Pounds of 12.5%. All right. So let's go ahead and start off by putting in our pie. We need our feed. And again, we're just going to go in pounds because this is a disinfection of a well site. So I'm going to label it in pounds. It's going to be volume measured in million gallons. We need our dose in parts per million. In this case, it's milligrams per liter. And the weight of water is 8.34 pounds per gallon. So now, the well is 300 feet in depth and 10 inches in diameter. The water table is 75 feet below ground level. If the desired dose is 80 parts per million. We'll put that right there. How many pounds of 12.5% sodium hypochlorite solution are required? Well, I need to determine the feed in pounds before I can attack the purity of it. I need the volume in million gallons. Let's start with the volume. So volume in million gallons of the well. That's going to be, and this is a big cylinder, so 0.785 times the diameter in feet, multiply that by the diameter in feet, multiply that by the depth in feet, and multiply that by the weight of water, 7.48 gallons per cubic foot. Well, let's start with 0.785 times the diameter. What's the diameter? The diameter is 10 inches in diameter. Well, 10 inches is not the same as feet. I need the unit of measure in feet. So let's calculate the diameter. Diameter in feet equals, the pipe is 10 inches, 10 inches over 1 divided by 12 inches per foot, and that's going to equal 0.83. 10 divided by 12, and that's going to give us 0.83 feet. So this is 0.83 feet over 1. We're going to multiply it by the diameter again. 0.83 feet over 1. We have the depth. Oops, I want a comma there. Depth. The depth is 300 feet. But the water table is 75 feet below ground level. That means we're going to have to put in depth in feet equals 300 feet minus 75 feet. The depth of the well is 300 feet. The water table is 75 feet below ground level. Quick math, 300 minus 75 gives us 225 feet. 225 feet. So let's write right here, 225 feet over 1. And that leaves us with 7.48 gallons per cubic foot. .785 times 0.83 times 0.83 again times 225 times 7.48, and that gives us 910.14 gallons. Now we need to take those gallons And we need to convert it to million gallons, right? Take these gallons, we want to convert it to million gallons. How do we do that? Well, let's make sure we're getting all of this. We have the depth, 300 feet minus 75 feet is 225 feet. That's what gives us our depth. When we multiply this across, we're getting 910.14 gallons, which we need to convert to million gallons. So million gallons equals 910.14 gallons divided by 1 million. Take that number, we're going to divide it by 1 million, and that's going to give us 0.00091 mg. But we're not done yet. 0.00091. So we're going to take that number, 0.00091, we're going to multiply that by 80 times 7.48, and that's going to give us 0.54. And that is at 100% purity. But we're using sodium hypochlorite, which is a liquid. It's bleach. It's an industrial strength bleach, not the 4 or 5% bleach that we get from the grocery store. We want 12.5%, right? So let's do feed in pounds equals 0.54, which is at 100% purity. That's here. We're going to divide that by 12.5%. If you take 12.5% and convert that to a decimal, what you're doing is you're taking 12.5, dividing it by 100, and that's going to give you 0.125. So 0.125. 0.54 divided by 0.125, and that's going to give you 4.32 pounds. 4.32 pounds. Let's double check this. I want to make sure I did this right. 0.00091 times 80 times 7 point. 0.00091 times 80 times 8.34. 0.61. Look at that. I'm going to leave this mistake here. I got 4.32 pounds, which is real close to A. It just threw me off because it seems like a little far away, but you know, that's the correct answer is A. But if I use 7.48 instead of 8.34, then 0.54 is not really the correct answer. The correct answer is 0.00091. So if this is 0.6 divided by 0.125, that gives me 4.86 pounds, which is a lot closer to A. I'm leaving that there. I want you to see that sometimes we make mistakes in math. And if you have an alarm going off in your head, if you're not sure, go back and check it. I feel very strongly, and I think most of my students agree, that when it comes to the math, following these steps, this method helps you see each step individually, helps you get the correct answer. Now it's time for me to ask you to like this video. Please subscribe to my YouTube channel. Please comment. Make fun of me, compliment me, doesn't matter. If you have questions, I'm going to do my best to answer those questions. I work a lot of hours. I run field operations for a water wastewater utility, which means all conveyance, everything from the well site to the wastewater plant. That falls under my area of responsibility. So please look for my link below the video. It goes to my website, and on that website you can download all the assignments. You can download, there are several downloads that are available for a small fee. I think it's worth it to download, to print them off, to practice, to follow my videos. Give me all the airtime I can get. And we're building a feature to include PDHs, professional development hours. Look for more information on that on my website and on YouTube. Thanks for being part of this.